means you have 2 is also a little outer. So you can say 3, 4, 5, 6 are actually closely related to, I mean, they're very close to the data. But if you look at on the right hand side, even 5 is actually away. The data is actually towards the right. If you look at it, the data is away. So what you have is 3, 4 and 6. If you look at 6 also, it is actually away. Therefore, either 3 or 4 are closely representing the data. And I think 4 is actually representing the data better. Line number 4, this is your line number 4. It is representing the data better. Now, why do you say that it is representing the data better? The simplicity, you call this representation as the model. From this data, the data has been plotted and the trend in the data has been captured using a function f of x, which is a straight line here. So using a function f of x, whatever might be that function, that is called the model. So the trend in data has been captured using a model. So this model actually is a regression model. The function f of x could be a straight line or it could be a curve, it could be a parabola, whatever. F of x can be anything, right? It can be a linear function, it can be a non-linear function. The straight line is a linear function, so you call it as a linear regression model. Any doubts in this? So what function f of x you are choosing, depending on that, you can actually predict what will happen in future also. If it is a straight line, you just need to extend the line and then say any point over the line is my prediction. What is the truth is something different. Over a period of time, the samples have been collected and this could be the similar trend in future also. That's what you're trying to say with a simple line. Lot of examples. For example, petrol and diesel rate, what is happening today? It is in a rising trend. Sudden fall in that rate cannot happen immediately without any major policy decisions by the state and central governments. So we know that it is going to increase only. As of yesterday, it was 97.5. So it is expected that, it is predicted that the rate will go to 100. It is a very natural prediction. That is your linear regression because it's in a rising trend. So linear regression cannot capture the trend in very complex data. So you can see here all types of all types of regression models, that is the function, which function f of x you are using, different types, how it is going to capture the trend in data. You can see here. You see here, not this one. Yeah, this one. This is a quadratic function. This is also capturing the trend in this data. As you look at the data plot itself, we know what kind of function f of x will be suitable. You can see here, and there is another example. No. Okay. So these are different, which we will come to that. So this is the basic idea of regression, capturing the trend in data using some function f of x. The simplest function that you can choose is a straight line. It is a linear function. So using scikit-learn, you can directly use linear regression. From sklearn linear model, import linear regression. So the function f of x is imported and you tell what is the x and y values. Since it is a straight line regression model, you can actually specify and then the prediction will be displayed. So you can see here 4.215 and 2.77. What is the value of A and what is the value of B? A is the slope and B is the slope intercept. That determines the orientation of the line. If you change A and B, the orientation of the line will change. So from this, they've got the same value. When you predict a new value also, it's very easy to predict over this straight line itself. Now, how do you draw this line? How does regression work? You simply take the line. Okay, you're going to use a function f of x and a line, it's okay. How do you decide that the line should be, it's close to 4 as expected by us? I showed you, right? So initially it will start with maybe a line somewhere here like this. As you see here, initially it might start with a line something like this. Sorry. It may start with a line like this. Machine learning tells you to start with something like this. And then the actual data points are there, right? They have been plotted. From every data point, calculate the distance to this line. From every data point. Now, this is called as the error. Whatever we have to reduce this. Actually, ideally speaking, the line should pass through every data point, which is practically not possible because the data points are spread over. They are not over a single line. So what we should try to do is we have to fit. This is called as fitting a line. We would like to fit this line, turn its orientation in such a way that you have the minimum distance between the points and the line. Every line, see line number 1, distance from all the points to this line, vertical distance from the points to this line. See this kind of vertical distance, that will be calculated. So from all the points it will be calculated, and then that is considered to be the error. That's considered to be the error. Now in order to reduce this, what we will do is we'll slightly change the orientation, either to the left or to the right. When we turn it to the left, if we find that the distance between the points and the line is reducing, we will still turn it to the left. Continue turning it to the left little by little. So that's how you see here. This is what you see here. See, this red line is the initial line. You slowly start changing the orientation of the line. Finally, the change, right? The change is dependent on a parameter called eta equal to 0.02. Okay, the small change in orientation of the line. Value of A and B will depend on this eta 0.02. The change in A and B. So if you do a little more, if you want to do it, let's see, it's going very slow, right? First iteration, second iteration, third iteration, fourth, fifth, sixth, seventh, eighth, 9. After 9 iterations also, it is not close to the points. So what we will do is we will do the parameter, increase the parameter to 0.1. So what happens? It jumps, and after that it goes closer, and then you get actually a line, this line near 4 that actually represents the orientation required to capture the trend in data. If you still increase that parameter, now the lines are going away from data at the top. Earlier it was at the bottom, now it is at the top. So there is some optimal value. This is you will be learning this, learning this parameter 0.1, and you will understand what will be A and B. So this process of continuously checking, the iteration, you're going through the iteration and checking the distance between all the data points and the new line. You call it as, error reduction. So this can be represented as an optimization problem, minimization of error. Optimization. So why it is optimization is because the error can never be 0. Even if you see here in the middle picture here, the line is here, but there are many points away from the line. We are only trying to do a best fit. Best fit of the function f of x only is happening here. So there is some error left. So you can never have error 0, which means the optimization problem says you are approximating the error to, you're taking the error to the minimum. So it is a minimization problem. This minimization can be done using many techniques. One is gradient descent. The other one is stochastic gradient descent. So there are many optimization strategies to actually identify. So you need to do it fast, right? How quickly you're able to do it, that efficient is your algorithm. So to capture the trend in data, you will start from here and you will end up here. With eta equal to 1, you end up here. This is the learning process. So when the learning process is done, you know at the end of it, you understand what is the exact A and B value that captures the trend in this particular data set. For a new data set, either this f of x might be suitable or it may not be suitable. You may have to check that again. But for this data set, you have trained a model f of x, which is a straight line that captures the trend in data. This process of reducing the error and then reorienting the line, the best fit, finding the best fit, you call it as the training. So during training, as the error decreases, you reach a point where the error becomes minimum. After that, you can see that the error keeps increasing, which means you have to go back and reach the point where you got the minimum, after which the trend changed. So this process is called as the training error, as well as, I mean, the process of the minimum error that you get, no, that is your training error that is left, after the training. Now the training is over, because after that the error starts increasing. So now you have reached a point where you fix the orientation of the line. So once you fix it, you still have some error left, right? Error means the distance between all the points and the line that we have tested. So this distance, you can take Euclidean distance or Manhattan distance, or there are so many ways of calculating the distance. Root means square distance. There are so many ways of doing it. Mean square error, MSE, RMS, RMSE. So many things are there. So any one you take. So that error value that you have, you call it as the training error. Training error should be minimum. Now any new data you take, and then you see if this line is still representing that data also, you can use that as some test data. So whatever data points you have, some of them you keep aside for test data. The remaining majority of the data should be used for training, maybe 70%, and 30% of the points, data points, you keep aside. You can use the line and see one by one, you take the 30 data points and see if it is actually represented by this line. That is testing. So in machine learning, you have 3 stages. One is training, the other one is testing. You can simply say it is 2 stages. But during training, the optimization that you are doing is a major step. So the first step is actually fixing f of x. It should be a straight line, or it should be a quadratic function, or it can be a any other function you want. Whatever is the function you want to fix for this data, you can actually choose. It could be a spline, specific types. It could be a sine curve, it could be a cosine curve, whatever might be the f of x you want to choose. So that is the first step. You call that as the model. Now you have to train the model. Training the model requires that you initialize the orientation of the line. Some random initialization you give. So you have to choose a value A, choose a value B, as well as choose the change parameter. You call this as the learning parameter, eta equal to 0.1. So you can do 0.2 and 0.02 and then see how the training is happening. You do 0.1 and see how the training is happening. Do 0.5 and see how the training is happening. Then you know that using 0.1, so you have to do training multiple times to learn these parameters. So eta is a hyperparameter that you are learning. After that, after the training is done, you know what is A and what is B. So that line is the model, trained model for this particular data set. And then the method of, the change, error minimization technique using this parameter, there are many optimization algorithm, minimizing error minimization algorithm. There are many. So if you want to plot the error you're getting, see for this red line, the error will be very high. For the next line, the error will be little lesser, little lesser, little lesser. So as you go closer to the data points, the error is going to be lesser, lesser, lesser. At this, if the second block, if you see for eta equal to 0.1, you have reached the trend in data. But if the lines move away from the data like this, again the error is going to increase. So you have a parabola, something like this, a U-shaped parabola. If you want to plot the error, you call that as gradient descent. So I will show you. So this is actually a plot of the error. It first increased, it reduced, increased, reduced, increased, reduced, keeps on going. So you don't have usually you don't have a very smooth curve, but sometimes you do get a very smooth curve. So that is so it's something like this. Error values will go something like this. It will keep on changing like this. So it's like it will reduce and then increase further. The point where it is the minimum in this curve is where your A and B has to be fixed. This is what is the first technique of machine learning, your linear regression. So now we can actually change linear regression using batch gradient descent, or stochastic gradient descent, or mini batch gradient descent. These are all techniques how to minimize the error. How should we move the line or the function f of x in such a way that the error keeps reducing and then it increases after some point, so that you know where is the minimum. Usually the error will go up and low like this green line what you're seeing, it might increase, it might reduce, it might increase. So it's like an oscillation here. So you will get to a point where it is minimum, and that's where you have to fix your A and B. Okay. So if you look here for this data set, the blue curve is a better curve. The green one is an oscillating curve. This is a different f of x. Red line is it's another f of x, almost a line, right? So which one is better representing the trend in the data? If you see, will you take blue or will you take green? You're able to see my screen, right?
Yes, ma'am. I think the blue one would be the best, ma'am.
Yes. So you need to have a simpler function f of x. Not a very complicated. Higher degree polynomials you should not take, because prediction using the higher degree polynomials is very difficult. So today we have learned what is training. We would actually do computations in the theory class, but the idea needs to be driven in. So today we have learned what is training, what is testing, and what do you mean by minimization of the error. Okay. Now the next point that we are going to understand is, as you said, the blue line is not exactly going through every point in the data set. But the blue line tells you how the trend will go next. It's easier to find out. The red line is not capturing the trend at all. The green line is going through many points, but then you cannot predict what will happen next. So this is called as the fitting characteristics. The green line is going through every point means it is actually learning too much about the data. It's bothered too much about the local changes in data. So a bird's eye view of the data you won't get with the green function. The blue is only an approximation, so you should not be fitting the model very close to the data points. It should not go through every data point. If you want to actually generalize the model so that it will also capture the future trend, then it should be an approximation only. It should not be closely capturing the small changes in data, or it should not be going through every point in data. You call that as overfitting. You should not, you should not bother too much. Don't do too much work there. Do only a generalization. So a model should be a generic model. It should not be overfitting on the data. If you learn too much about data, you cannot move to the future. You cannot predict the future. So if you do this red line means you're actually not learning so much about the data itself. This is called underfitting. Underfitting also cannot help you the future prediction. It cannot also help you about future prediction. So overfitting or underfitting, both of them is not suitable for a given data set. You have to have something in between, the blue line. It should be a general model. It should be the best fit model. It will be the most generalized model. Best fit model is the generalized model, not the green one. That is overfitting. Red one is underfitting the model. Any questions here?
Hello, ma'am. Uh, if the
Yes.
data is in multiple dimensions and is, as you said, we can't visualize it, then how can we know if the uh, line is overfitted?
See, here you're able to visualize it. In the theory class, we are going to do it mathematically. Okay. For higher dimensions, we will only do mathematically, no visualizations. So mathematically, we will see how do you decide whether it is overfitting or underfitting, which is a generalized model. Actually, that will be decided only the error minimization, the optimization algorithm. That is one part. The other part, whether it is overfitting or underfitting, it's a generalization model or not, that will be decided using optimization only. We actually achieve that by error optimization only, minimizing the error. The optimization algorithm used for doing that, we achieve that. But if you want to ask me, is your question that, or are you asking how do you choose the blue model or the green model or the red model? Is that what you're asking?
Yes, ma'am. How can we how can we differentiate the green and blue line mathematically? That's what I'm asking.
Yes. See, the red line is ax plus b. The green line is x square, something like that. Okay, it can be a sin sin h function. There are other f of x functions which will come, higher polynomial degree models come like this, functions come like this, spline functions come like this. Okay, so this is like more like a parabola. The blue line is more like a parabola. Now f of x1, sorry, f1 of x, f2 of x, and f3 of x, three different functions are here. This is one, which model or which function, which pattern actually fits your data. Only by trial and error you can find out. Let's say, for example, let's say you chose blindly, you have chosen this red function, red model, and then you do the machine learning. Your error is always staying at 120. Even the minimum error using the optimization function is 120. if you use the function f of x, which is representing the blue line, your error is staying at 20. The minimum error comes to 20. If you are using green, the minimum error comes to 10, let's say. You understand what I mean?
Yes, ma'am.
You do machine learning using 3 different models. So 3 times you will do machine learning. But the error is least only in the overfitted model. So you should understand that, for this particular data set, the error at what did I say? 120, 20 and 10, right? Yeah. So at 20 is a more generalized model. So it all depends on the data set. There is no fixed rule for choosing like this. But from standard data sets, these ideas you can learn. That's all. Any new data set is given, you have to find out which model is suiting the best. Even after choosing a model, uh, the orientation of the model, that will be chosen by that will be decided by the optimization algorithm using the algorithm that you're using. There are so many optimization algorithms. You may have to try at least 2 or 3 of them to decide which one is the best for your data set, even after choosing the given f of x, even after choosing any one of this f of x. Is that clear?
Yes. Uh,
Go ahead.
we will always assume, like for linear regression, graded descent.
No, not clear. Okay, your audio is.
Ma'am, is it clear now, ma'am?
Yeah, it is better now.
Okay, ma'am, like for gradient descent related problems, we will always assume that a parabola is the best fit, right? Even if
No, this is the f of x that is fitting the data. Gradient descent is on the error values only. That is not plotted here. It looks like this is what I told you, right? The
so,
error will start at some point. After that, it may reduce or it may increase. If it is
so we can.
increasing, you will change the orientation to the opposite direction.
So we will take any point on the parabola and we'll just move from there one by one.
You will just move from there.
Okay, okay.
So that is a different plot. This is the data points. Gradient descent will be on the error points, error values. Error value in the
Ma'am,
y-axis, and then you have the distance in the x-axis. Yes?
ma'am, if we were to predict a new data point of, I mean, if we want to predict a new data point, if the best fit we choose is the blue line,
Okay.
the new value will be on the line, ma'am, or
On the line.
will it
It
be
will be only
on the
on the
line?
line.
Okay.
It will be on the line only. So it is an approximation only, but then it still works. For a given problem, if you have proper data set, or this prediction will be very close to the actual. So it all depends on the quality of the data set you have. If the data set that you have is very realistic, whatever trend you have model fitting you have done, that will help you do the prediction. For example, this blue curve that you're seeing, so that we find is the best model fitting here. So if the value of x1 is 1.5, okay, so you want to predict the value of y. So you perpendicularly go up and then point here. You will say that if x1 is 1.5, then y value would be 3.8 or something. I mean, it's is it 4 or not? I don't know, or around 4, right? This point is around 4. So you can predict that if x1 is 1.5, the prediction could be that prediction will be for y. X1 will be a known parameter and known value, and y1 you have to predict. So that's how you do a prediction. How accurate is this prediction? It will be on the line only. That's what you can do. But how accurate is the prediction depends on, it will always be an approximation. That depends on this data set, whether it is very realistic or not. Do you have good samples here that actually represent the problem? Then this prediction will be good enough. See, somebody would have predicted that, okay, even today they are predicting that the petrol prices will go up to 100, right? Maybe it will not go up to 100 immediately. It's possible, no? Or it may cross 100. That is also possible, right? You understand what I mean?
Yes, ma'am.
Yeah, so that's how. So you now you see any problem, given problem, any information you have about the problem, you should be able to represent it as data points like this. Only then you can use a machine learning model to actually represent the trend in this data set and do a prediction for the data set. Do a prediction for the problem. So if you want to apply machine learning to a problem, you should have some same sample data, or any information regarding the problem should be in terms of, in the form of some sample data points like this. We should first represent the problem as some sample, some information about the problem. You should represent it using some sample data points like this. Once you do that, then we can choose any of the machine learning model which is suitable for this data points, and then we can do a prediction for the problem. How can this problem evolve into, and then what values it can take? What values the data points may take. So there are so many things that you can apply in your, all the questions that you have in your mind regarding the ambiguity that you have in your mind regarding any problem in this world, you can model it as a machine learning problem, and the model will be good enough depending on how good is your sample data, the data points. How good is your data point? That good will be your prediction. For example, what will be the job opportunities in 2021 come this year? Till last year, what was the trend? And what is going to be the trend next is some prediction you can make. There are so many factors involved. If you look at this particular problem, what we are talking about, we are just talking about one factor, which is X1. So factor X1 is about the economy. The economy is improving, or it's going negative direction or positive direction, and accordingly job opportunities are increasing. So let us say x in the x1 in the direction is just one factor, economy, positive or negative economy, and y in the y axis is going to tell us the number of jobs you are going to get. Let's say so. Y values represent that. Let us say so. So for one factor, you can actually predict something. So whatever you're going to predict, this variable y is dependent on x. That relationship is captured using this blue function. That is what actually you're trying to do. X versus y. How the relationship among x and y, as x changes, how is y changing? That's what you mean by trend in data. When there is a change in x, how is it going to affect the change in y? That is what you mean by trend. That's what you're trying to capture here. So you may have so many factors, x1, x2, x3, x4. Putting them all together, how will y change? If all of them change, how will y change? Using regression, it's actually a very easy mathematical calculation. You cannot visualize it because then x1 in one axis, x2 in another axis, x3 in another axis, x4 in another axis, so it becomes a, and y in the fifth axis, so it becomes a 5-dimensional space. The problem will get into a 5-dimensional space. That is also another advantage of machine learning. Any amount of higher dimensions, you have a suit, if you choose a suitable model, you can actually fit that into that data points. That's possible. Only thing is graphically you may not be able to visualize, but then mathematically, algebraically, you will be able to fit the model, and you will be able. So a function with one variable x, f y equal to f of x, y can also be equal to f of x1 comma x2, f of x1, x2, x3, x4. It's possible, right? You can have multivariate functions. So when I said data set, univariate and multivariate data sets are given, no? What we have seen here is a univariate data set. What we are seeing here is a univariate data set because the function y is dependent on just x1. So f of x1, y equal to f of x1. Multivariate means x1, x2 at least will be there. At least two variables will be there. More than two variables can be there. So mathematically, we will be able to work out the function f of x values. And then, so it could be like, a x1 plus b x2 plus c x3 plus d. Possible. So you can choose a model, something like that, and fit it on the data. And while fitting it, reduce the error, right? That's how you say the model is fit. Then you test the model. Once the testing is done, if the testing error is also very close to the training error, your model is a good model. So that's how you choose a model for a given data set. So univariate data sets, if you choose one, you can plot the data points first like this in blue color according to this code, and then you can you can put all these three models and see what happens to the data set, which one is actually fitting the model better. Sometimes the line can fit the model better, so that's something you can do. So if you look at it, the data set, once it is given, you have to first split it into training and test data set. Fit your model, train your model using the training data points, and then test it with the test data points. Then you're done. It's ready for prediction. So any doubts here? We will stop with this today. Any doubts here? Anybody else?
Ma'am, I have one doubt left.
Okay.
Can we go to the NETA,
Which one you want to see?
the hyperparameter, ma'am?
You're able to see,
The
right?
Not yet, ma'am.
You're not able to see it? Okay. You are seeing it, right?
Yes, ma'am.
Okay.
So, ma'am, for a given data set, how can we select the best value of NETA without actually trying different
There
values of
is no,
NETA?
no. There is no standard rule to identify the eta by default. Only by trial and error it can be found out for any data set.
So, ma'am, if the data set is very large, then we have to
No,
try
after
for
some a
various
few
values of that.
iterations only.
Then
After few iterations only, you can still see that the error is changing very slowly. Then you can increase the step size. What do you mean by eta equal to 0.02? The step size, the change in A and B for the line f of
shifting
x
the
is very slow, right? So the step size is what you're increasing here. After a few iterations only you can change eta. You don't have to go through the entire process.
So will it be dynamic in a single iteration? So initially, when the line is at 0, that is the red line, till we gone through the 2, we kept it as 0.2.
See,
Then we
you
suddenly change
still,
it to
you
0.1.
see, even
Can we
if you
change it
have eta equal to 0.02 a step size, you will still reach the correct line at some point, but it will take a longer time. All you have to see is it taking a longer time to come close to 0 or not? That's what you need to see. For that, 2-3 iterations or 5-6 iterations should be fine. After that, you have to stop and change the step size.
Okay. Okay.
What happens here is if you change the step size to 0.5, actually your error is increasing in the opposite direction for eta equal to 0.5. So immediately you understand that the eta value should be greater than 0.02 and less than 0.5. So it may be good to have 0.2 also. This is what you have to do it only by trial and error. For every data set.
Okay.
That cannot be automated. I mean, you can even this process you can automate. That's all. You may have to set a threshold or a time limit, and then, but otherwise, whether it's algorithm or you doing it, only by trying it out, you have to fix the hyperparameter value.
Yes, ma'am. Got it, ma'am.
Okay. So nobody else has questions, huh? Only just 2-3 people are asking questions. Others have understood, is it? So I will ask you one question. So do you think that the regression model, a curve or line or something, is suitable for any data set?
No, ma'am.
The higher dimensions, lower dimensions, anything okay. So have we reached the ultimate model that can actually predict the trend in data? Is this regression is the only way in which you can do it? Or do we have other ways of doing it for prediction? Okay, so this is a question we will answer in future. And thank you for today. Sorry that I missed that to remember that the lab was there today. I was thinking 9:50 I'll be having class. That's how I registered in my mind. So the whatever data set you have downloaded, you download the univariate data set, take that data, take the x and y values from that, and then do the same plotting what I have shown you with that code. Please try that as homework. Okay.
Okay, ma'am.
Yeah, you can even give some random values to see whether it is you can give your own random values and try. Yes, Uma Shankari,
No, ma'am.
you have something to say?
No, 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 no.
Okay, thank you. Thank you, guys.
Thank you, ma'am.
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 Thank you, ma'am.